Hey everyone, welcome back, and today let's solve Leetcode problem 763 titled Partition Labels. So we're given a string S and we want to partition the string into as many parts as possible so that each letter appears in at most one part. And so note that the partition is done so that after concatenating all the parts in order, the resultant string should be S. So we have to return a list of integers representing the size of each of these parts. So essentially we want to maximize the length of our output array that actually contains the different number of sizes or of the different number of parts or partitions that we have of our input string S. So as you can see in example 1, our input string S is inputted as AB, and that long character string, which I won't actually say. And we'd output a list of the 3 different partitions and their corresponding lengths of how we can actually split or partition this input, right? We'll have first a partition of length 9, then we'll have a partition of length 7 and a partition of length 8. And note that, of course, this does not have to be sorted or serialized in any necessary order. So the reason why we actually output lengths 9, 7, 8 of our corresponding respective partitions is because the partition is AB, AB, CB, ACA. And essentially what this does is every single letter in this partition won't appear in any other next partition that we actually make in the future, right? And that applies here as well, right? When we have D, E, F, E, G, D, E in this second partition, none of these letters are going to be present in the future partitions or the one behind it, okay? And of course, then we'll have H, I, J, H, K, L, I, J, because any of these letters are not present in any of the other partitions that we actually make in this array, or input string, rather. So this is our partition so that each letter appears in at most one part, or at most one partition. And a partition like A, B in the long string, H, I, J, H, K, L, I, J, is incorrect because it splits into less parts. So although this is valid, right, each and every single letter or element is only appearing in one partition, we can actually split this into 3 partitions, and we have to maximize or optimize the number of partitions that we actually want to split our input string S into so that each element or letter only appears in at most one part. So in example 2, we have the input string S to be ECC, DEC, and we would output 10 because, as you can see, there is no way to actually partition this input string S in any ways so that one letter is appearing only in one partition, right? And you can go ahead and just brute force the solution and try different things out, right? But we have this E, okay? And so until we get to this next E, we can't make another partition, right? We can't just have one partition of length 1 to just be this singular E, because then we'd have an E in the next partition, which is not allowed. And so until we get to this next E, we have to include all of these letters in our partition. But since we already have a C as well, we have to actually include the C as well, and so that's the entire length of this input string S, and so we can only partition it into one possible partition, which is the input string S itself, right? We can actually split it into different halves or thirds or so on and so forth, and so in that case we just output the length of the input string S itself, which in this case would be a length of 10, which is basically the only partition or way we can split it into, right? Just no splits. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem. Okay, so the first thing that we want to do is, as you guys have seen or noticed a pattern of in many of my Leetcode videos, we're going to be using a hash map, right? We essentially want to store every single element in the input string S with its last index, or basically the last time it actually appears in the input string S. And we can actually do that very easily in Python using the enumerate built-in keyword or iterator. So I'm going to say for I and C in the enumerate of nums, or sorry, I think there should be S, right? I'm so used to just looping through arrays called nums in Leetcode that it's like a default structure for me. But for I and C in enumerate S, we want to set our final to be, we'll set final at C rather to be the index I. And I actually have to declare that final hash map up here. And essentially, why I named it final is because this hash map maps every single character in the input string S with its final occurrence, or basically the indice that it appears last in the input string S. Okay? And so I'm going to call it final for that specific reason. And essentially what I'm doing in this enumerator keyword is I'm looping through the keyword and corresponding every single character with its corresponding indice. And so I set final at that character C to its corresponding indice I as its key value pair. But you still might be confused on why this actually sets every single element with the last indice. And the reason why is this actually gets updated every time we see a C or every time we see a character until we don't actually see that character itself, and will ultimately store the very last index or position of that character in the input string S with its corresponding key value pair in the hash map. And to better explain that, let's say we're actually enumerating or looping through the input string S for example 2. First we see an E here. And so we'd store final at value C to be corresponding with index 0, because we see it at index 0 right now in this iteration of that enumerator function. Then we'll move on to C, and then all these values in between. And then we get to E again. Okay? And so we've already stored E in our hash map to be equal to 0, right? We know that final at value E is going to be equal to 0, but we see it again. And now we'll set final at value E in this iteration to be the I, which in this case is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. So we'll set final at E now to be 8. Of course, the value itself doesn't change, but the key pair actually does change. It gets updated for this new iteration because we see it again, and so we want to update it with the larger indice, or basically the indice that marks its last occurrence in the input string S. So once we actually store that for IC using the enumerate function, and to better visualize this, I'll just print out final for you guys. So when I actually run this, you'll see what it actually outputs. So for this example, in example 1, actually it was example 2 because it's a little bit easier. E is mapped with 8, right? As we talked about before, the final occurrence or indice in the input string S to be 8. C is mapped with 9, the last indice that it actually appears at. B is mapped with 6 because that is the last indice that you see B in the input string S, and D for that reason is mapped with 7 because that is the last indice in the input string S that you will see as 7. So now that we actually have that, let me just delete this line. Now we want to actually loop through the input string S and form partitions at the very last element using an end variable for every single partition. And so I'm going to initialize 3 variables here. I'm going to initialize a resolution array, which will be initialized to an empty array, which is essentially what I'm going to be returning. I'll initialize a size, basically the length of the current window or the current partition that I'm building up in this iteration of our enumerator of our list, or string rather. And then I will initialize an end, which is basically going to store the very last indice for every single character C as we actually loop through the input string S for every iteration or size length for every partition of our input string S. So I'm going to set res, size, and end to all be initialized to an empty list and 0 and 0 respectively, because of course size and end are going to be initialized to integer values of 0 because I haven't actually traversed through the input string S yet. So now I'm going to use enumerate again. I'll say for I and C in enumerate again. In the enumerate of S, I'll basically increment the size by 1 because that shows that, okay, great, I have seen one more value or one more element in this current partition, and so I want to actually increment the size of this current partition or window in this iteration by 1 because I've seen one more element. And then I'll set my end variable, or basically the last indice of this current partition of the very last index that we want to see for every character C in this partition. I'll set it equal to the maximum value of course, itself, because we don't want to make it smaller, and of course, the last at that index C for this iteration. And now we actually have to have our validation to check that if the current indice I that we're looking at in this iteration of our character C matches that ending indice, or the very last indice for any character C in the input string S or in this partition. So I'll say if I is actually equal to the indice value end, we know that we've found a valid partition. So we want to add the size of that current window. So we'll say res.append size and reset the size to be 0 so we can actually use it optimally again for the next partition, because of course we don't want to add on continuously that size for future partitions as that would be incorrect. And ultimately we can just return res because it will have eventually stored every single length of every single possible partition at the end indice for every single partition and input string S, and so we can simply return res. And so unless I made any syntax errors here or I spell something wrong, this should be accepted. Okay, actually name my hash map to be final. So now they should be accepted. And as you can see, this is just about as efficient as you can get. So to kind of recap what this code does, I'll initialize that final hash map on line 3. Then I'll actually use an enumerating keyword or looper iterator for my input string s and store final at character c to its last indice or last position where it actually occurs in the input string s. Then I will initialize my 3 variables that I'm actually going to use to store and accurately monitor the current partition, with res, size, and end being res being initialized to an empty array, which I will ultimately return, size being basically monitoring the current size of our current partition in this iteration of our input string s, and end being basically the very last index of any character c in my current partition. And once I actually enumerate through all the characters again in the input string s, I'll increment our size by 1 because of course we've seen one more element in our current partition, and I'll set end to be the maximum value of itself because we don't want to make it smaller, and final at any indice or at any character c in this partition, which will ultimately store the very last indice that we want to go up to for any character in this current partition. So our base case essentially is if the current index for any character c actually hits that very last indice end, then we know we've found a valid partition with no possible characters being repeated in any future partitions, because this is the last occurrence of any character c in this current partition, as we saw with its indices final at c, or basically the I value, and so we'll append that corresponding size to our resolution array and reset that size for this next partition to be 0, because we don't want to overcount for future partitions and future iterations of the array, or string rather, and we can ultimately return res because it would have stored the lengths of every single partition of our input string s. So for the runtime complexity of this problem here, as you guys can see, this is going to be big O of n time, because of course we just enumerate through the input string s twice, and so technically this would be big O of 2n, but since coefficients really aren't a big deal in runtime complexity, this would just be simplified to big O of n. And of course, memory complexity wise, as you guys can see here, this is going to be constant time, because again, we're not really using any extra data structures. Of course, we're kind of using a hash map, but since we're actually enumerating through it and we're just looking it up, it's really going to be constant time because hash maps and hash sets have constant time lookup. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.